Okay, right. So we are just recalling some stuff. Okay, right. There's this thing called Boyle's law. Okay, now Boyle's law, it basically boils down to P1 divided by 2 divided by P2 is equal to V2 divided by V1. Okay, and then also P1 P2, that's just original and final pressure. V1 V2, that's just original and final volume. And then T1 T2, that is just original and final temperature. And then by looking at this equation, we can actually express it as P1 times V1 is equals to P2 divided by V2, simply meaning V2 in this case will be equal to P1 times V1 divided by P2. Okay, that is equation 1. And then now if we continue, this is what is referred to as Charles' law, also known as the law of volumes. Please note, it's an experimental gas law. Okay, it basically talks about how gases tend to expand, simply meaning an increase in volume when heated. Heat just means a variation in temperature. Okay, now note, pressure is constant. So whenever we are talking about Charles' law, the law of volumes, which is speaking to volume and temperature, it's important for our pressure to be constant. Now, what does it mean when we talk about a constant pressure? Simply meaning your final pressure is equal to your initial pressure. Okay, now, if that is the case, mathematically speaking, V1 divided by T1 is equal to V2 divided by T2. Okay, now, for us to derive or to get our second equation, it's actually V2, which is equal to T2 times V1 divided by T1. Now, if we look at this over here, it's referred to as a PV, okay, a pressure volume diagram. Simply meaning, on the y-axis we have pressure, on the x-axis we have volume. Now, we will notice that there's a graph over here. We will also notice that there's another graph over here, okay? Now, these two graphs, they basically depict Boyle's law graphically as well as Charles's law. Okay, simply meaning Charles's law, pressure remains the same, pressure 2, and then what's happening? V1 V2. Okay, and then as we can see here, V1 P1, okay, V2 P2, okay, right? And then that's Boyle's law over there, right? Okay, right, so long story short, from that we can now say equation 1 is equals to equation 2, simply meaning V2 is equals to V2. Okay, right? Now when we say equation 1, here's equation 1, and when we say equation 2, this over here, this is our equation 2, right? And so now we get P1 times V1 is equals to P2 equals to T2 times V1 divided by T1. Okay, right? Now, long story short, another way of writing this down there is by simply saying P1 times V1 is equals to T1, and that is equals to P2 V2 over T2. Now, okay. When I am writing this down, there's actually something that I'm trying to point out here. Okay, simply meaning there's something for us to look into here. Look at the structure. Okay, look at the structure. This is P1 V1 P2. This is T2 V1 T1. Okay, so this is PVP. This is TVT. Okay, now look at the structure here. PVT. PVT. Okay, right now, there's a reason for that. The reason for that, or the mathematical significance of that, is when we get it in this form, then we can actually say simply meaning we can refer to the PVT relationship as a type of constant. Okay, why do I say type of constant? Because there are also a bunch of other constants out there. However, if we can mathematically manipulate this formula into this form, and now we have it in this form, essentially speaking, we can now refer to that structure as a type of constant, but for a specific gas under specific conditions. Okay, simply meaning if that is the case, then we can refer to this as a characteristic gas constant. Simply meaning we will now go and then we will say R is equal to PVT. in words, we can refer to this, nah? We can refer to R as characteristic gas constant. Okay, right? When the mass of a gas is considered, then this is the case. Then we can say mR is equal to PVT. Okay, now please note what I'm going to do now. Nah? What I'm now going to do is the following. I'm going to manipulate this formula, and then after manipulating this formula, we are going to actually get what? PV is equal to mRT. Simply meaning we just multiply this side by T, multiply that side by T, and then now we get this. Okay, right? This is the characteristic equation for a perfect gas. So now we are going to say here, characteristic equation for a perfect gas. Right? So now we have that. Okay, now since this foundation has now been laid, okay, this foundation has now been laid, now we can move over to what is known as the specific heat capacity of a gas. So let me just write that down. Okay, right, I'm going to write that down. Specific heat capacity of a gas. Okay, right, specific heat capacity of a gas, okay, equal to the ratio of the heat added to or removed from a gas to the resulting temperature change. Okay, it is equal to the ratio of the heat added to or removed from a gas to the resulting temperature change. Okay, so let's just write that down. Okay, right. When we talk about the specific heat capacity of a gas, it is equal to the ratio of the heat added to or removed from a gas to the resulting temperature change. Okay, right, now let's go further. There is something there called specific heat capacity at constant volume. Okay, simply meaning specific heat capacity, but we are going to qualify it stating at constant volume. This is the amount of heat transferred when the volume remains constant and the temperature changes by 1 degree. Okay, simply meaning at constant volume, the amount of heat transferred when the volume remains constant and temperature changes by 1 degree. Okay, then also we have specific heat capacity at constant pressure. Okay, right, this is constant pressure. Now this is the amount of heat transferred when the pressure remains constant and the temperature changes by 1 degree. Simply meaning there's a mathematical way of looking at this. Okay, there's a right, here's the ratio Cp divided by Cv. Also note R is equal to Cp minus Cv. Okay, right. So this is where we are going to stop for now. So these are, or this is the conclusion of our thermodynamic laws. There's 5 of them. Specific heat capacity of a gas happens to be the conclusion of those 5 thermodynamic laws, if we may put it as such.